Hello everyone, I am Dr. Radhika, working as Senior Assistant Professor in the Department of VNR VJEC. In today's class, we are going to see an ideal transformer, practical transformer, how to draw the phasor diagrams for both no load and also on load. So before we directly go into any practical transformer, we have to talk about what is the condition of an ideal case. So a transformer is said to be ideal if it satisfies the following properties. The first property is it should have no losses and its winding should have zero resistance and its leakage flux should be 100%, so that the flux produced by primary completely links with the secondary, and where we can also say if no losses and 100% if it is leaking, we can also say 100% efficiency as far as ideal transformer is concerned. And the last point is the permeability of the core should be so high that negligible current is required to establish the flux in it. But in practical transformers, ideal transformers we can't see. But before directly dealing about the practical transformer, we'll be starting from ideal transformer, how it looks like and how to draw the transformer, ideal transformer under no load. So for an ideal transformer, the primary voltage V1 is same as the primary induced EMF V1 as there are no voltage drops. So this is the transformer representation. V1 and V1 and E1 should be equal and V2 and E2 will be equal. So whenever an alternating voltage is applied to primary, it draws a current, and that current is all about your magnetizing current, which is represented with Im, and that always lags the applied voltage by 90 degrees. And in all these, in a transformer, we know that flux is the only quantity which is linking with both primary and secondary. So here and the current that produced will always magnetizes the core, and definitely it will be in phase with the flux, and it will always lags behind the applied voltage. So definitely your V1 should be in this way. In such case, it will be lagging the applied voltage by 90 degrees. So this alternating current time produces the flux which is proportional to and in phase with it. The alternating flux links with both the windings, and hence the EMF E1 will be in the primary induced and EMF E2 will be induced in the secondary phase. And as per Lenz's law, this will always, the amount of EMF induced will always oppose the cause of producing it. So that's the reason why V1 will always be in opposition with E1. This is all because of the Lenz's law. And depending upon whether it is a step-up transformer or step-down transformer, this E2 magnitude will be decided. If here we get E2 and here if it is a step-up transformer, definitely E1, next E2. If it is a step-down transformer, E2 and here this E1. So this is how we represent an ideal transformer representation. Next, this is so magnetizing current which always magnetizes the core. As we presume that in case of an ideal transformer there are no losses, 100%, like the flux linked, it will links with both primary and secondary, so it is lagging. And now let us consider about practical transformer on no load condition. So the vice versa of ideal transformer is all about your practical transformer. A practical transformer differs from the ideal transformer in many aspects. In case of as we said, there are no losses, but no doubt in a practical transformer, the winding which was wounded, it exhibits the property of resistance. So definitely primary resistance R1 will be existing and the secondary resistance R2 will also be existing. And 100% efficiency, which is quite impossible because input will always be equal to output plus some kind of losses, So these are iron losses, the winding resistance and magnetic leakage, which gives to your leakage reactance. So here, when we are talking about the practical transformer on no load, so initial will be doing with this. Let us consider this is our primary, and here we will be the values. These are all your no load components, X naught and this thing, and this is your I2 dash and this is your primary current. We'll speak about this I2 dash in the next session. So here in ideal transformer we 100% talked about only this magnetizing component, but the moment we started about the practical transformer, we have to talk in terms of reality and where this resistance will also exist. So because of this, i.e. the current we have represented with this, and as it is representing this, we have considered it as your magnetizing current, and resistor component will always be in phase with the voltage, primary voltage Vp, and the resultant of these two, Im and Ie, will gives rise to your no load current, So this is how we have vectorial addition of these two, we got I naught. The maximum value of no load current I naught will be around 3 to 4% of its full load current, and the angle between the primary voltage and no load current is represented with phi naught. So this phi naught is said to be your no load phase angle, and also we can get IE is equal to I naught cos phi naught and Im is equal to I naught into sin phi naught, and finally we got I naught is equal to root of this thing. So this is how we can also calculate your no load current, and the amount of EMF induced in the primary is represented with your E1 and E2, and in as far as ideal transformer is concerned, we have considered V1 and E1 were equal and V2 and E2 were equal. Now we have switched into the topic of practical transformer, where we have to see all the components individually, and here in this, the no load current of a transformer I naught is given as 10 amps at a power factor of, the no load power factor angle is 0.25, which is lagging, and when connected to a 400 volts 50 hertz supply, your primary current is 400 volts. And calculate the magnetizing component of no load current, which is all about your Im. We can calculate, we have already deduced from the derived and this we have taken as E, and this is the so obtained V1 and I naught, this we have taken as this. So this is a right angle triangle. So Im is I naught into sin phi naught. We can also calculate using this equation. And iron losses. So we have the primary current, no load current. As far as in practical transformer, definitely we have to talk about your losses, because we know that input will never be equal to output when we are talking about your practical transformer. Output plus losses. And again, in these losses, we have to talk about no-load losses, which are supposed to be called as fixed losses. So actually, in practical transformer, iron core causes hysteresis and also eddy current losses when it is subjected to an alternating flux. When designing the transformer, the efforts have to be made to keep these losses as minimum as possible. So these hysteresis losses can be reduced to a larger extent by using high-grade materials as silicon steel, and eddy current losses can be reduced to a larger extent by using thin laminations or thin stacks of laminations. So even as far as no load current is known to you and primary voltage is known to you, our iron core losses and no load losses can also be calculated by using this thing, because as we are talking about active power, we know the active power is VI cos phi. So that V represents your primary voltage and that current represents your no load current, and that phase angle between this V1 and I naught, which is all about your phi naught. So this is how we can also calculate the iron losses. And also maximum value of flux in the core. Maximum value of the flux in the core. This also we can calculate using the same equation. And this is all about when your practical transformer was working on no load current, because initially when we start our experiment, when we are talking about a 115 by 230 volts transformer whose rating is 2 kVA, by using the auto transformer, we will be giving the input to your transformer 115 volts and 230 volts, and initially we make sure that initially your transformer should work under no load condition. It has to be switched on under no load condition. The moment when 115 volts is given to your primary, definitely on the secondary V2 side we can see 230 volts, and initially during your first stage when your transformer was working under no load condition, the ammeter which was kept on your secondary side will reads nothing because it's been open circuited, secondary been open circuited. That is what we called as no load condition. So this point has to be determined and it has to be observed while conducting your experimentation, which is all about your load test on single phase transformer. Right. Next we have to see all about your practical transformer on load. So there are different types of loading conditions which we call them as resistor loading, inductor loading and capacitor loading. There are resistor loading, inductor loading and capacitor loading. So when a transformer is loaded, the current I2 starts flowing through the secondary and the magnitude of the phase of I2 is determined by the load. If load is inductive, definitely I2 lags V2. For inductive, I2 lags V2, and if it is of capacitive, I2 leads V2, and if it is of resistive, I2 will be in phase with V2. So there exists a, when secondary current starts flowing, because in previous we have seen the first reading has to be observed under no load condition, slowly we will be switching on the load. So when we are talking about the resistor loading, the load current depends upon the type of the loading. So as I2 starts flowing through your secondary, and when it starts flowing through the N2 number of turns, when it starts flowing through here, we will be having N2 number of turns, and here we will be having N number of turns, and this is your V1 initially supply, which is of AC. So there exists a secondary MMF N2 I2, due to which the secondary current sets up its own flux phi 2. This is your main flux which will be in opposition, which then this phi 2 flux will always opposes the main flux which is produced due to the core, due to the magnetizing component of no load current. Hence this MMF N2 I2 is called demagnetizing amp turns. This is called as demagnetizing amp turns. So this flux I2, the so established this flux I2 momentarily reduces the main flux, due to which the primary induced EMF E1 also got reduced. Hence the vectorial difference is increased, due to which the primary draws more and more current from the supply, and this additional current drawn by the primary is due to all of the load, and hence this is called as load component, and this establishes the flux phi 2 in such a direction that opposes your main secondary produced flux. So because of which we can also say that transformer is a constant flux machine, because of which, and this is said to be your the flux that is produced, which is all because of the extra load that has been drawn, and is your I2 dash gets neutralized with your N2 I2, and here by using this N2 by N1 into I2, N2 by N1 is your K into I2. So here the load component of is K times of the secondary load current. So I2 dash is said to be the load component of primary current, and this I2 dash will always will be in 180 degrees phase with this secondary current. And how can we get our primary current? How can we get our primary current, which is all about your I0 plus I2 dash. This is how we can determine our primary current. So here we will be talking about the phasor diagrams of a practical transformer on load condition. So here, so moving on, this is your flux, and I'm not drawing your IM and IE, because of which we got your no load current. This is a no load current, and this is your E2, and let us consider for a resistor loading. So as resistor loading on the secondary side, I2 will be in phase with E2. I2 will be in phase with E2. So I2 dash, which is about the load component of primary current, will always opposes this 180 degrees phase shift, 180 degrees phase shift, I2 dash, and in order to obtain your primary current, we will be vectorially adding I2 dash. Which will be getting our I1. This is for resistor loading, and the angle between V1 and I1 is said to be your primary power factor phi1, where phi0 is said to be your no load power factor angle, and phi1 is said to be primary power factor angle. So this is for resistor loading. So let us consider about inductor loading. Let us consider inductor loading, where your I2, as we are talking about the inductor loading, I2 lags E2 by an angle of phi2, and here I0 we have drawn very small amount magnitude, I2 dash 180 degrees phase shift, and by adding I2 dash and I0 we got our primary current I1. Again, the angle between your primary voltage and primary current is said to be your primary power factor angle phi1, and the no load angle is your phi0. And this is all about your capacitor load. Initially we have done with resistor loading, inductor loading, and capacitor loading. So as we're talking about the capacitor loading, I2 leads this by an angle of phi2, I2 dash 180 degrees phase shift, and I0 very small amount. The angle between V1 and I0 is said to be your phi0, no load power factor angle, and by adding I0 and I2 dash we got our primary current I1, and the angle between V1 and I1 is your phi1. So this is how we got to introduce the load component of the primary current, which is all about your I2 dash. And even for different loading conditions also, we have drawn the phasor diagrams of a transformer on load condition. So we are going to see equivalent circuit of transformer and how to draw the phasor diagrams. So this is how we will be representing the equivalent circuit of transformer on load condition. So on the secondary side, we have represented a different type of loading. So N1 primary number of turns, N2 secondary number of turns, primary resistance, primary leakage reactance R2, secondary resistance R2, secondary leakage reactance X2, and your primary input voltage V1, and this is your secondary terminal voltage, primary induced EMF and secondary induced EMF. So here, before we start up for going with the phasor diagrams for different loadings, here we have to write down the equations where initially the primary current that is passing through your R1 and X1, so drops definitely I1 R1 drop and I1 X1 drop need to be considered. So here, as we know, even from ideal transformer we got no, because of Lenz's law, V1 and E1 will be opposing from each other. So here I am writing V1 is equal to minus E1 plus I1 R1 drop plus I2 X1 drop. So this will be considering as the first equation, and coming to your second loop equation, E2 is equal to your I2 R2 plus I2 X2 plus secondary terminal voltage. So this is how we'll be writing the equations, and using the same we are going to obtain the phasor diagrams for different loadings. And one more thing, using this R1 X1, this is an impedance triangle, so here we can consider this as Z1. So E1 is equal to minus E1 plus I1 Z1, and this E2 is equal to V2 plus I2 Z2. Impedance, in terms of impedance we have taken, right? And before we go and start with the for drawing the phasor diagrams, we know that E1 will always opposes V1, and I1 drop will across the resistance, which will be in phase with I1, and I1 X1 drop across the reactance, leading the I1 by 90 degrees. And V2 is said to be the terminal voltage across the load, and I2 R2 drop will be in phase with I2, and I2 X2 the drop across the reactance, which will be leading I2 by 90 degrees. And the points to be considered for drawing the phasor diagram. So initially we have to consider the flux as reference. Let us consider for an inductor loading. So here we consider the flux as reference. And the no load current, we know I0, and this is our E2. The first point to be considered, the first flux as reference, E2 E1, and E1 lags your flux by 90 degrees. And how to obtain minus E1, and E1 E2 will be in phase, and for this we have to assume V2 in a particular direction. For this we have to assume V2 in a particular direction. So let us consider for inductive loading. So for inductive loading, I2 lags V2. I2 lags V2 by an angle of phi 2. Here we have drawn I2 and the angle between V2 and I2 is phi 2. So here we'll be trying to obtain final E2. We know that E2 is equal to I2 Z2 plus V2. So along with this, I2 R2 90 degrees, I2 X2 to Z2, and this becomes your E2. And I2 phase shift, I2 dash, we have I0 and the phasor I1. So again we have primary we can obtain as minus E1 plus I1 Z1. So here I1 R1 90 degrees I1 X1. So this is our I1 Z1, and from origin we'll be getting our V1. So this is how we can obtain a practical transformer and equivalent circuit of transformer phasor diagram for different loadings. And this is how we can also obtain for resistor loading, inductor loading, and for capacitor loading, current leads voltage by angle of phi 2, I2 R2, I2 X2, I2 Z2, E2, and this thing minus E1, I2, I0, I1, I1 R1, I1 X1, and primary for different types of loadings. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.